Okay, so hey everyone. This week we're going to go over a data structure, which is pretty cool. It's called segment trees. If you want a link to the slides, hopefully this link should work. I'll give you a few more seconds to write this whole thing down. Oh, I guess people are having issues with access. So I think if you have a UCLA email, you should be able to.
Okay, it should be fixed. I just switched the permissions a little bit.
Okay. Okay, so I assume it's working for everyone. Okay, let's just get started then. So yeah, first of all, what is a segment tree, right? Well, the high level description is that it's a data structure that can do range queries and also support modifications. So if you guys remember like sparse tables from week 2, that sort of supported the same operations, but a segment tree is much more powerful in the fact that it can also support modifications. And we'll see that the range queries that it can do go beyond just max and min, right? So what we have is that we have O of n preprocessing, and then also O of n log n querying and log n modification as well. So you can tell that this data structure can be extremely useful. And in I don't know, if you come across any problem that has range querying or modifications as well. So the basic idea is that we're gonna create a tree where each node in the tree basically stores some value for a segment of the tree. And by segment, I mean like a range. So let's just do an example. I think that's probably the best way of clearing it up. You can basically ignore this picture. I just put it in so there is a picture in the slide. Instead, we can go to the whiteboard. And let's just see what a seg tree could look like. So let's say we have an array that has 8 values, okay? I'm choosing 8 because, 8 is a good number for binary trees, and that's what a segment tree is. So we have this range 0 to 7 as the root. And what we do is we essentially split off into smaller and smaller segments. And they're essentially halves of the parents. So we get 0 to 3 here, 4 to 7 here. And if we continue, we get 0 to 2 or 0 to 1 here, 2 to 3 here, 4 to 5 here, and 6 to 7 here, and like the individual elements as well in the leaves. So you can imagine how if we wanted to, let's say we're doing like a sum query, like range sum query. And our array was like, I don't know, something easy, like this is our array, right? And let's say, I don't know, we wanted the sum for the range 0 to 3. Okay, so what we can do in this case is actually we start at the root, right? And we just check if the root is like completely contained in our query interval. So in this case, 0 to 7 is not. And we can similarly like check each child. And we see that like 0 to 3 is completely contained within it, right? So, and then like each of these nodes will have the answer for each of these segments. So in this case, we have 6 here, like stored at this root, and our answer is just 6. And then like if we go to the other child, which is 4 to 7, we can see that like 4 to 7 is not like fully contained, and like it has no overlap with our query range 0 to 3. So we should just, forget that side. And what we return is the answer is like 6, right? So this is an easy case because our answer ended up being a node that we actually calculated beforehand. What if we gave like a harder range, for example, right? Like what if we gave some 0 to 4 instead of 0 to 3? Well, this is slightly harder because now no node in this tree contains the answer to this query. What we have to do instead is that we have to, well, first of all, we do the same process. We look at the root and we're like, oh, it overlaps with our range, but it's not contained within our range. So we move down to the children. We take the left child and we see that it's fully contained in the range. So we take the answer, which is 6 in this case, and we don't proceed further with the children. And then when we go to the right node, right, we see that there is some overlap with 0 to 4 and 4 to 7. And like the element or like the range 4 to 4 is like the overlapping range, right? But we can see that it's like not fully contained. Like 4 to 7 is not fully contained in 0 to 4. So again, we go to like the children here in this case, and we can disregard 6 to 7 because it doesn't overlap with our query range. And we just continue going down until we get to like just the 4 spot, right? And the answer there is 4. So when we finally calculate it, we just add like 6 with 4 since we're doing a sum operation, and we get 10. Does this make sense so far? Like how exactly, given like a tree with all these values, how you would like query this tree with any possible range and it will give you the correct answer within log time. And the reason I say log time or log n time, where n is the number of elements in the array, is because we're pretty much like finding ranges, right? Like it's not like our range 0 to 4 is going to be composed of like 5 different subranges in our tree, right? In this case, our subranges were 0 to 3 and 4 to 4, and that's only like 2 ranges. And like you can always build a query range with like log n subranges. Like the worst case scenario, for example, is like 0 to 6 query range, and we have to like compose that with 3 different ranges, right? Because like if we have 0 to 7, this is immediately solved by just checking the 0 to 7 node. So essentially, like you only have to get to log n different nodes in this tree to answer any query. Okay. Anyone have any questions about this? Anyone want me to like clarify anything? Repeat anything? Yes, no, nothing? Okay. So it seems like at least 2 people know what's going on so far. Yeah, again, this is like not the full explanation. Like a lot of this will probably make more sense once I get into like how you actually build this thing, or like and also adding in like the modification part. So let's just get into like the pre-processing part, right? Like how would you calculate all these values? An easy way is you first like build out this tree. Like it's not hard to build, like you just keep splitting into half every interval until like you can't, like when there's only one element, right? And then how you actually build this tree is like you can do it bottom up. First of all, note that the number of elements is O of n, right? Because like the reason why it's O of n is because you have like n nodes on the bottom, and then n over 2, and then n over 4, all the way up into the root node, which is 1, right? And like this is like a geometric series sort of thing, which sums up to like approximately 2n, right? So the number of nodes is O of n, which means that like this can be stored in O of n memory. Let's get rid of that. It's kind of weird. So how do we build this tree? Well, like, first of all, you can just take every element's value. And in this case, I set the values to be exactly what the nodes are. So hopefully it's like a little, I'll put the values in red. Right, and we can just do like a bottom up DP sort of thing. For example, we're building this segment tree for sum queries. So we just like sum the children at every single node. Up until the root, right? Wait, that doesn't make sense. Does it? Did I
Is this
mess
a
up the
sum?
summation? Yeah. Did I not sum
So
something
it should be
correctly?
like 28.
Oh, my bad. I summed 5 and 6 instead of 4 and 5 here. Yeah. Okay. Okay, now it should be fixed. Okay, so yeah, you can see like you can like do a very easy bottom up DP if it's like a sum. Let's say it was like a min or max. It's also very easy because like you can just do the min or max at every single node based on the children. I think that that's probably like the main queries. Like you can probably do special stuff. But like this is like the basic idea. Like in general, you want to be able to support an operation that you can easily build up on. So you can see that like the pre-processing is like clearly O of n, right? Like we just like go to each node one time and calculate the answer and store it. So we have like O of n pre-processing, right? And then we have O of log n query, range query. That's like so far what we've done. Because like once you pre-process it and like you only have range queries, then it's just very easy to query it by like recursively going to each node and checking if it's like contained in our query range or not. And the last operation we want to talk about is modification, right? So modification in this case is actually very simple. Let's say we wanted to modify, okay, we're talking about like element-wise modification. So we're talking about modifying one element in the array. Let's say we wanted to change element 4 to 0. All right, so we're changing this 4 to a 0. Well, like this is also easily supported by this sort of tree because we can just go to element 4 in this tree, change it to a 0, and then just propagate like this change up to the root, right? So like now our answer for its ancestors are all wrong. So we can just like recalculate. We get like 5 here because it's 0 plus 5. We get 18 here, and we get 24 here instead of 28. So if we look at this tree again, it's now again fully correct at every single node. Like if you query it again, it's not going to give you the wrong answer. So you can easily tell that this is log n because we only change the number of nodes in like the height of the tree, and the height of the tree is log n. So hopefully this makes sense so far. Again, any questions from anyone? Maybe we can do like a poll. Everyone can see the poll, right? Is it working? Okay, cool. Okay, so this is like a very basic idea of like what a segment tree. Well, it's not basic. Like this is like pretty much what a segment tree is. And like it's super powerful because there's like so many operations you can do, and like it actually shows up a lot in problems. So it's good that everyone seems to mostly understand. Okay, so I guess next we'll talk about, see what the slides have. Yeah, we can talk about range modifications, right? Like you might be wondering, why can we only do element-wise modifications? Can we like go further and do range modifications like we do range query, right? Does anyone have any like ideas? I mean, some of you definitely, but anyone have a naive idea for range queries, or sorry, range modifications? No? Well, I was thinking like, I don't know, maybe for range modifications, you just run the range or the element modifications like for every single element in the range that you're trying to modify. It's like all right? It's like sort of bad, but I mean at least you can do update like range updates. So the actual smart way, or the actual answer to this is yes, like we can do range modifications, and we can actually do them pretty quickly as well. Yeah, and the answer is like something called lazy propagation. And we're essentially being more efficient by being lazy. And yeah, so the slide sort of says like what it is. The basic idea is instead of like, you can imagine a range modification. Let's say our range modification is we're adding 5 to all the elements in range 1 to 4, right? So instead of pushing all the changes all the way to the leaves, like you can imagine that this is like at least O of n, because what if our range was the whole array, right? Then you'd have to update at least all the leaves. So instead of doing that, we try to push them down the minimum amount. And you might think that like this update basically leaves a tree that isn't right. Like if we only push it down, if our whole tree is up, like our whole array is updated, and we only update the root node, like you might think that like queries on other ranges might be like incorrect after these updates, but we will see that they're actually it's actually pretty smart. So yeah, let's just do another example, but this time with range modifications. So I will draw a new tree, I guess. Let's say our array was all zeros initially. All right, okay. Let's say we decide to do an update on the range 0 to 7, okay? And our update says we're gonna add 1, right? So our array should become like all ones, right? But our tree, if we were not doing lazy propagation, what would end up happening is that we're trying to add +1 here, right? And we have to propagate this +1 throughout the whole tree. Or actually, in this case, the answer would be like +8 here, you know? And it'd be like +4 here and +4 here, like +2 here and +2 here, and like +1 and all the way, right? And this is like O of n time. So instead of that, what we're doing is that we're gonna stop at 0 to 7. It's like similar to like the querying thing. We stop, like if you remember in the querying, when we queried for 0 to 3, we didn't actually go down all the way to the leaves 0, 1, 2, and 3, right? We stopped at this node that contained the range 0 to 3. So it's like a similar idea here. We're just stopping whenever the range is like fully contained in this update range. So in this case, if we're updating 0 to 7, we stop at the root node, which is 0 to 7. And what we're doing is we're gonna add a new value that says, we'll call it lazy. We're gonna say +1 to lazy. Okay. And this is essentially telling us that we need +1 on all the elements contained in this range. Okay. But like, we're actually not going to update these in this update because we don't need to. We'll update it whenever we actually need to. And that happens when we query, right? Like for example, if we query for the value at 0, we're going to have to update it because we don't want to return 0 when we actually updated the whole thing with +1. Yeah, so in this case, we store like a lazy equals +1, right? And let's say we do a query on just like the range 0 to 0, right? So if we use the same implementation as our normal seg tree, we're just gonna check this range 0, right? And we're gonna just spit out the answer 0, which is wrong because our answer should now be 1. So the question is like, how can we get this answer 1? And what happens is when you query 0, 0, right? You start at the root 0 to 7, and you see that, oh, the lazy value is +1 at this node. And this tells us that we have to update stuff below this. You know, we have to update the range 0 to 7 somehow. So what we end up doing is like we propagate this lazy, right? We propagate this lazy down, and we actually get rid of it at the root. So this becomes back to 0. Right. So again, we're querying 0 to 0. So what happens is our right side is untouched because we're done with it, but our left side just continues this propagation. So what ends up happening is that this lazy value. Also, one thing you should note is that like once you propagate this lazy down, you have to add like the value at this node. You add like, you know, +1 times 8, I guess in this case, because there's 8 nodes in this range. So the answer here becomes 8. And we can see that this is the correct answer because again, our whole array is just ones and there's 8 of them. So we can just continue to propagate this lazy down. And while we propagate it down, we add, or like we update the node that the lazy value was propagated from. So what ends up happening is that lazy becomes, so when we propagate this lazy down, right? So originally lazy was +1 here. And then when we change it to 0, because we're like continuing to try to query for 0 to 0, and 0 to 0, 0 to 3 is not contained in 0 to 0. So we just want to continue to find the nodes that actually compose our query. So we change this to 0. And at the same time, we update the value to like 4, right? Because it was like, +1 times 4. And originally it was 0. And if we continue to do this, right, what ends up happening is that we get to this node again. So again, this thing becomes 0. And it propagates down to the children. Actually, okay, the children, yeah, okay, it's fine. They can contain lazy values, but yeah, I guess it's fine. So what ends up happening is that all the values that are updated, you can see are like this node, and this node. And then again, in like this node, we can see that the value should become 1, right? So we're essentially just doing like the same thing that we did with range query, and the fact that we're just trying to find the nodes that compose a range. But at the same time, we're pushing down this lazy value. And this lazy value is the representation of the update that we should do on all the children, of this node. And we can see that like because it's the same thing as our range query, like it should also be log n time, right? And it also gives us the correct value because we've propagated all the lazy that we need to propagate for every single node that composes our query range. Like in this case, our query range is 0 to 0, and we propagated all the lazy above it down to this node. So this node, should be correct because we've propagated all the updates that need to be propagated down to this node. So what ends up happening is that we get our answer to be 1 because of these propagations and the corresponding updates as we propagate. And we can see that there's lazy values throughout the tree. Like this node and this node still have to be updated with like a +1 below it. But we don't continue propagating these nodes because they don't matter to us in this query. We only care about 0 to 0 in this case. And these nodes have nothing to do with 0 to 0. They're completely separate, right? They're disjoint. And we can leave them for other queries that we want to do. If other queries actually overlapped with 2 to 3 or 4 to 7, then we'd actually have to push down these lazy values. But for this query, we don't. So there's a question in the chat. Oh, wait, no. Oh, this is a long time ago, I guess. Oh, I didn't even see you guys' ideas. That's my bad. Yeah, they were good ideas too. Okay, hopefully this example sort of made sense. I guess I made it a little easy because my update range was actually just the root node. We can do an example where the update range isn't just the whole array. So I guess okay, first of all, does anyone have any questions about what I just did?
So how come, I guess maybe this is obvious to you, but how come you never end up applying the operation twice? It seems like when you do the update step, right, you apply the operation that you had stored up in lazy, and then you push it down to the children.
Mm-hmm.
Now, what if the next time you want to update that parent node, you're going to query the children, then do something with that, and now you've done that lazy operation multiple times. I don't 100% see why you don't do it multiple times.
I'm not sure if I fully understand what you mean, but if we wanted to update, you're saying if there was another update on the root. Yeah. So
yeah.
So there's another question in the chat that says if you wanted to update the same range multiple times, yeah, you just continue to add to the lazy value. For example, let's say we wanted to update the range 4 to 7, right? We just add to the lazy value here. If we wanted to do -1 to the range 4 to 7, the lazy value here would just become 0. Because we're just adding -1 to it. Wait, so Jacob, I don't know if that answered your question.
No, that wasn't my question, but I think I see what the answer to my question. It's you're not recomputing the the actual value.
Yeah, you're just
yeah.
adding to it. You're adding to it. Right.
Yeah. Okay, a follow-up question, how do you implement this thing?
Yeah, so we can get to that, but like for now, for implementation, like you can just like create like a node struct, right? That stores a value and like left and right child, and also like a lazy value, right? And then like you essentially do what I described. Like, I mean, you also have to contain like the range in the node. So you have like a left and right value that represents the range. And in a query, you start at the root and you do it recursively, right? So you check if like this range is contained in the query range, and if so, just like return the value. So I'm talking about querying in this case. If it's like not contained, or like if it like overlaps, you like propagate the lazy while updating the value of this node. And then you like continue into the children. So it's like all recursion because it's like pointer based. Someone posted an implementation in the chat. Honestly, I would recommend, I mean, you can look at the implementation. I feel like reading other people's code. Yeah, I would recommend trying to write it from scratch and like using someone else's implementation maybe as like support. But like the concept is just like it's recursive, and like the checks that you have to do are just like checks on the ranges, like overlapping and like contained. And also like propagating the lazy as you like I guess you can like have like a, I don't know, like an extra argument that says like, oh, we're propagating this value down to this current node.
Okay.
Yeah, like I can't give all the details because like there's just a lot of details, and it's better if you just like look at code or just like try it yourself, right? So I'm not sure if everyone understands lazy propagation. Does anyone want me to do like another example, or like have any questions about like this update? Okay, I'm gonna just put out a poll. And yes, the poll is anonymous. We're not going to track you down. Is this a bug, or has no one actually voted?
I think 8 have voted. Wait, I can share the results.
Okay, I think that's a bug. Like it says 0 out of 9 people voted for me. Okay, yeah, let's do another example. This tree again is kind of a mess. Okay, I'm just gonna clear stuff from this tree and like do another better example, hopefully. I wish there was a way to clear like only like red text. Okay, hopefully that should be good. Yeah, let's do a better update. Let's say I'm doing something like, it's a good example. I don't know, 3 to 5. Right. And again, we're just doing +1. Okay, so how do I do this better? We can have like, okay, I'm just gonna write lazy as, it's a good variable name, L. Right, so we're gonna have the lazy value initialized at 0 at every single node. And like, again, for all the leaves, it's like, it's whatever, because like any lazy value there, you could just add it directly onto the value itself. So Tony asked, should I implement this tree once and keep it in my code template? Yeah, I would not recommend coding this during a contest, especially like lazy propagation. For the earlier example, where we didn't have range modifications, I feel like it is pretty easy to code it during a contest. Although, again, you don't have to, you can just like, use a template. My implementation, I actually don't use like the node and pointer stuff. I use like an array. And like the array represents a tree where like a parent is like the index over 2, So this can easily represent this tree. And you can see how like, I guess the querying function is a little hard. But like the building the tree, you can see it's very easy because like you just put all your initial values in like the back half of the array, and then you can just like do a for loop from like n to 1, calculating the answer based on the children, which are like 2 times the index and like 2 times the index plus 1. Hopefully that gave you like a better idea like of what like the array implementation will look like. For lazy, it's a little harder with arrays. I think it's better to implement with like the nodes and like pointers, just because it's like conceptually easier to understand. Okay, so back to this update. So we have 3 to 5, and what we do is that we're like, again, it's like the same as query, right? So we look at the root, and we see that 0 to 7 is not contained in 3 to 5, but they overlap. So we just like continue on both of its children. 0 to 3 and 4 to 7, again, both overlap. We go to the children. We see that like 0 to 1 does not overlap at all, but 2 to 3 does. So we continue down to the children of 2 to 3 because 2 to 3 is not contained in 3 to 5. And we get to like the nodes that we end up getting to are, we use a better color maybe. We get to these 2 nodes, right? So again, this is our update function. And we essentially get to these 2 nodes. And what we're doing is we're just updating the lazy value at both these nodes. It's like pretty simple, in my opinion. Like, I guess one thing that you might have to do is that you also have to like propagate the lazy value as you're doing this. But for now, essentially what we're doing is we're setting the lazy value to be +1 here, and we're updating this one to 1 here. And our tree, again, okay, I guess the root lazy ones don't really matter. It's just the value itself, it becomes +1. So I'll let the values be in green and lazy be in red. So all of these have 0, mean, everything should have 0 because they're initialized to 0. So this is the state of our tree after the update. Hopefully this makes sense. Now let's say we're querying for okay. Okay, one slight thing, actually, I think I didn't say this earlier, but in your update, you also have to propagate it actually upwards. So, and the reason why is because let's say you're querying 0 to 3, right? We're just gonna get to this node and we see the answer is 0. Like there's no propagations because all the lazy values are 0. And our answer is just gonna be 0, right? Which is wrong. The answer should be 1 because our array is 3. Our array should look like, so I'm missing a 0 here. Nope, nope. Okay, my bad. Our array should be this, right? So the query 0 to 3 should output 1, but our query outputs 0. And the reason is because during an update, we should also be like propagating this update upwards. And like what this should look like is that we're just propagating this v equals 1 sort of thing. Like we have an update here, right? That we know that there's an update. And we're just like adding 1 to all these values, pretty much. And like the same thing here, we're like adding 1 to everything above these nodes. So this actually becomes plus, oh, whoops, not adding like, you know, the number of elements in the range times the update. So this should actually be like +4 here and like +1, wait, no, that doesn't make any sense. Sorry, should be +2, my bad, because it's 4 to 5. So this should become 2. And then this should become 1 + 2, which is 3. So our tree's values should be correct above the nodes 3 and 4 to 5. Like below it, you can see that these two nodes are wrong. Like these two nodes have the wrong values, like they should have value 1. But everything above our nodes in the update range should be correct. At least that's how I think about it. And for queries, again, you want to make sure everything as you propagate becomes correct down to this range. So when we query 0 to 3, there's actually no propagations going on here in this case because all the lazy values are 0. So in the query is pretty boring in this case. We just come down to this node, no propagations again, and we see the answer is +1. Or the answer is 1, which is correct. So again, I want to repeat like the basic idea here. When we update, we get these nodes that compose our range. Again, similar to our like range query sort of thing. Like we get a bunch of nodes that compose our range. And we want to make sure the value above these nodes, like the values at all of these nodes, which I'll mark in blue, we want to make sure all of these nodes above our range are also correct. And the reason is because if we queried if our query used one of these nodes, they actually have to be correct. Like for example, if we didn't actually update these nodes correctly, and then we queried 0 to 3, we would get 0 back, which is the wrong answer, right? So we want to make sure everything above is correct. And when we query, the basic idea is that we're propagating all these lazy values down the tree. And the nodes that we end up getting should all have the correct value because of all these propagations. And because we know that everything is correct with these lazy propagations. Let's say like our query was on 4 to 4, right? Like in this case, there actually is lazy propagation because we end up going, okay, I'm gonna get rid of the blue circles. Let's say our query was 4 to 4. So we started this node and then we go down to this child and then we go to this child. And then again, since there's a lazy value here, we propagate +1 here and +1 here. And then this becomes, this value here becomes 2, not 0, because our lazy value has been updated or it's been propagated. So we can, this lazy value is reset back to 0. And our query results in 1, which is the correct answer because of this propagation. Yeah, so it's a little more complex than like the base version of the seg tree. But essentially what you're doing is that like the main concept here is that first of all, we're not gonna, update everything that we can. We're gonna update as little as we can. And we're only gonna update stuff through lazy propagation when we actually query for nodes that need to have values propagated down to the nodes. And I think another main idea is that like every range is just like a bunch of nodes in the tree and like not too many nodes, like log n nodes, right? And these nodes are like at, like in this case, like 3 to 5 was the node 3 to 3 and 4 to 5. And we're essentially just trying to keep the values above these nodes correct. So that like when we actually query for nodes above, like the values are going to be right. And like this, like keeping them correct is not hard because you can see that like that there's not too many nodes above our range. Like as I circled earlier, there were like 4 blue nodes that I circled that were above our update range. And in general, like there's not too many nodes that you need to update with the correct value because lazy propagation handles like the rest of it. So I guess like, does anyone have any questions? Again, feel free to ask anything. It is like a difficult concept. I personally like did not understand it that well for a long time. Maybe I'll release another poll. Actually, I don't know if this poll is that useful.
Yeah, I think a lot of people don't, even though it's anonymous, put like the explanation was clear,
Yeah,
even though they don't understand it. Like I
true.
think maybe we should change the wording to like do you understand it, and not like, was the explanation clear? So then you don't feel like
Uh-huh.
you're like insulting the person who's presenting or something.
Well, I mean, also like I feel like asking the same questions again on like a re-explanation is also like, you know, like people don't want to insult.
Yeah,
the
There's that
like
too.
like explained it 2 times and I still don't get it. Like you're not good at
Yeah.
explaining.
Just how like when you're getting your haircut and you ask the barber to like do it again for like the 3rd time, it gets awkward. I think in beginner track, the polls that have been actually effective are ones that like have some content related to the thing. Like it'd be like a little quiz, and then often like everyone will like say they understand it or something, but then you give the quiz and like a third of the people get it wrong, and then you know you need to go back over it.
Interesting. All right, quiz. Actually, I don't really have anything. Yeah, I don't know. It's like a pretty tough concept. I think you need to implement it. Hopefully this will give you an idea of like the basic concepts, because implementing it is like pretty difficult as well. But it's like not as bad if you like understand the concept.
Is there like an invariant property of the lazy seg tree? Like, can you say, oh, like I was thinking it would be something like there's some like clean vertices and like dirty vertices, and then like for all clean vertices, like the value plus the lazy value like is correct or something like that. But I feel like that's still like missing something because that doesn't say anything about the dirty ones. Like,
Well, I mean, they're like, first of all, like the clean ones are always going to be above the dirty ones, right?
yeah.
I mean that gets a little weird because like you can get lazy values of 0 because like, you know, 2 updates canceled each other out. Okay, question. How would you do range minimum / maximum query with segtree? Yeah, so we don't actually need range, or we don't need lazy propagation. Like we can just use like this segtree, and like we actually don't even need updates too. Like this is like too powerful for RMQ. Like you just like pre-processes in this tree, like all the answers to like every single segment in the tree, and a range query would just solve like the range minimum / maximum query. Like because all the answers should be correct in the pre-processing. There's no updates. And like the range query will just find we'll find like log n nodes that compose your range. And like you just like take the max or min out of all these nodes. So I would say yeah, I mean, I guess like if you wanted to, you could use a seg tree for RMQ, but you know, there's other ways of doing it. Like you could use a sparse table. You could use you can use a Fenwick tree. Actually, no, you can't use a Fenwick tree. My bad. You could
Yeah,
use
you can't use Venn.
square root decomposition. I guess we haven't talked about that, but yeah. So I mean, okay, the answer is yes. You can use a seg tree. I'm actually not sure. Like, given a range minimum query, like I actually might use a seg tree, just because like the array implementation is super easy. Super easy as in like low number of lines of code. Like figuring out the array implementation is a little difficult, but if you have it memorized, it's very easy. Or if you have it copied, you can paste it very easy. Yeah, I don't know. I don't know if there's anything else. Actually, the slides has a slide that says something about implementation. So like the picture I attached is like a representation of sort of like how you do it in an array. So like every box contains the array index and the range that it represents. And you can see with like an array of length 16, it's like pretty easy to represent in an array. And like the example that it's showing in this case is the range 3 to 10. And you can see like the exact nodes that come out. Like we have the node with just 3, and then we have the range 4 to 8, and then we have 8 to 10, and then we have 10, right? And the other implementation I mentioned is with nodes and like recursion on like children. Yeah, so someone sent a Codeforces log entry, yeah, where this image is from, and that's a pretty good explanation. But again, I think the node one is just like easier to come up with. Like the final result of the array one, like the implementation is a little tricky. Yeah, like with lazy propagation, like the array one is like pretty difficult. Like DS is data structure.
Oh.
Yeah, so Justin does it with a pointer based. There are advantages for pointer based. Like, for example, if you, I don't know, never queried part of the array or never used part of the array, like the pointer version like helps you save memory. Because like let's say you actually never query for the node with just 3. Like you don't have to actually construct that node. Right. Like you can just have, yeah. Like you can just have the parent. And I think like 2D seg trees use like the pointer version. I would have no idea what a like 2D seg tree looks like in an array. That just, I don't know. Maybe I don't really understand 2D seg trees that well, but I mean 2D seg trees don't really come up. Yeah, hopefully this was like a good introduction into seg trees and lazy propagation. There is a problem set. I will say that it's a little harder than usual, I think. Especially if you've never actually implemented a lazy seg tree. Yeah, attendance code does not exist actually because I was lazy.
Wait, for real though? It is lazy.
Yeah.
It's been fixed.
All right. I'll make the attendance code right now, actually. Anyone have any suggestions for the code? No?
But don't we already have a code?
Oh, do we actually have one?
Isn't it
Oh.
lazy?
Oh, is it just lazy?
Yeah.
Oh,
It
okay,
is,
cool.
yeah.
Never mind. Oh, I guess we created all the events beforehand. Is that right? That's a good idea. Wait, why do I see 2 events? Why are there 2 events? There's one. Do other people see 2 events? Am I tripping? Oh, there are 2 events, right? Are we given the code for both of them? Boosting everyone's points. Okay, yeah, there's nothing else to cover. So again, like ask any questions that you have. I should probably stop recording.